Look at question 22c from the 2013 revised higher physics paper, and it states that a crash test dummy has a mass of 75 kilograms. Just going to highlight that as an important piece of information, and is wearing the seat belt. During the collision, the dummy travels a distance of 0.48 meters. I'll highlight that as well, while coming to rest. Calculate the average force exerted on the dummy by the seat belt. It may look at the beginning of this that you're not given a huge amount of information, but we have information in the previous questions. So I'm just going to make some space here, and we're going to try and use that space to solve the problem. So the first thing I want to do is write out everything we know, and then we can try and find out what we can use to solve this problem. First of all, the mass of the dummy is 75 kilograms, and the distance it travels is 0.48 meters before it comes to rest. We also know its final speed. It comes to rest, so it's 0. We know its initial speed is the speed of the car originally, which was 13.4 meters per second. And that's about it. We're trying to find F, the average force exerted on the dummy in coming to rest. And one of the nice things about physics is trying to solve problems. Really, that's what I enjoy doing, and that's what all these videos are based on. We need to find the force, and it doesn't look like with this information we can do that. But the simplest formula for force is F equals ma. So if we know the mass, which we do, and we know the acceleration of the dummy, we can find the force. In this case, that acceleration is a deceleration. We have some other information though about the dummy in terms of its motion, and we can use these three pieces of information, with the formula v squared is equal to u squared plus 2as. An equation of motion which incorporates all of this data with acceleration. So we'll plug the numbers in now. The final speed is 0. The initial speed is 13.4 squared plus 2 times the acceleration, which we're trying to find out, times the displacement of 0.48. And we can rearrange all that to get a... It's quite difficult to do that sometimes, so I'll just do that here. We take this number and we want to get rid of this from this side. We want, in fact, to only have a. So let's subtract that from here. So we must subtract it from here as well. So it's minus 13.4 on this side. So minus 13.4 squared on the other side is equal to 2 times a times 0.48. And then we want to leave the a here and have everything else gone. So this is a is multiplied by all of these things. So let's divide everything by 2 and 0.48. So we must do that on this side as well. So that becomes minus 13.4 squared over 2 times 0.48 is equal to a. So when we solve that, we get a value for a, which is minus 187.04 meters per second squared. And so now we have a and we have m. So we can use the formula above, Newton's second law, to determine the average force. So that is F is equal to 75 times our acceleration, 187.04, and we get a value which is this is a minus value of acceleration of minus 14,028 newtons. Now bear in mind, just before we finish here, that we wouldn't get full marks for that because it's 3 more significant figures, 0 to 8, than any of the values in the question, which are just a 2 sig fig. So we should write our answer to 2 sig fig. So we can write it as 14,000 newtons, or we can write it as 1.4 times 10 to the 4 newtons. So that's the problem solved, but that is only one way of solving the problem. So I'm just going to put a line down here and give you another option. One of the other options that are given in the solutions is to think of this problem from the point of view of energy conservation. So if we do that, we can tell that this dummy has a certain amount of kinetic energy to begin with. Its initial speed is 13.4, so it has an initial kinetic energy, and that initial kinetic energy is going to be turned into heat. as it slows down to rest. That heat is done by work done by the seatbelt and bringing it to rest, and so all of that kinetic energy is turned into heat by work done by the force applied by the seatbelt. So if we write down below that what these equations are, so we've got half mv squared is equal to the force times the displacement. So the v here is actually the initial speed, which is 13.4, so we can plug the numbers in. A half times 75 times 13.4, that's the initial kinetic energy. 13.4 squared, sorry, is the initial kinetic energy, and that's equal to the work done by the seatbelt, which is the average force of the seatbelt times the displacement the seatbelt, the dummy moves and coming to rest. So if we rearrange that by bringing this over to this side, then we get the force to be the same as before, 1.4 times 10 to the plus 4 newtons. Okay, so that's the second method. But of course, this is physics, so there is indeed a third method. So I'm just going to put another line across there, and we'll try the third method now. In the third method, we can consider the equation impulse Ft is equal to the change of momentum mv minus u, like that. And we know m, the mass of the dummy, we know the final speed 0, we know the initial speed 13.4, but we don't know the time of the collision, and we don't know how long it takes to come to rest. But again, we can use another Suvat equation like we did over here to determine that, and that Suvat equation is that the displacement is the average speed, u plus v over 2. The two speeds added together divided by 2 will be the average speed multiplied by the time. So it's the time we're determining, so we can plug our numbers in. 0.48 is equal to the initial speed, 13.4, plus the final speed of 0 over 2 times t. And if we do that calculation and rearrange for t, we get a value of t to be 0.072 seconds. So that's our time, and we can then plug that into this formula to get f. So f times 0.072 is equal to the change of momentum. And this is the mass of the dummy times its final speed, 0 minus its initial speed, 13.4. And rearranging that, all of that, as you might expect, gives us the force on the dummy, which is again 1.4 times 10 to the 4 newtons. So there we go. That's why I love physics. There's so many ways of doing the same thing. Just to summarize then, the simplest way, the way that's possibly the most common, is to use F equals ma, but we must determine A using an equation of motion. Alternatively, you can use impulse, but in this case you have to determine T again using an equation of motion. And then probably the most unique method is using conservation of energy. And again, it's relatively simple, but it's applying the laws of physics that energy is conserved and it turns from kinetic energy into heat by doing work. So hopefully you've understood at least one of those methods, and you'll be able to solve problems like that in the future.